The accelerating universe. We thought we understood how this was supposed to work. After the Big Bang, the universe exploded outward in every direction. Matter and energy scattered into the void, everything flying apart from everything else at tremendous speeds. That much made sense. The initial explosion provided the momentum, but from the moment expansion began, gravity should have been working against it. Every particle of matter pulling on every other particle, slowing the whole thing down, acting as a cosmic brake. For decades, this was not just an assumption. It was the foundation of cosmology. The universe was expanding, yes, but it had to be decelerating, losing speed with every passing moment. The only real question scientists debated was how much deceleration was occurring. Was there enough matter in the universe to eventually stop the expansion entirely? Enough gravity to reverse it, pulling everything back into a catastrophic collapse? A big crunch? Or was the universe just barely light enough to expand forever, but more and more slowly, asymptotically approaching some final state of stillness? Think of it like throwing a ball into the air. The moment it leaves your hand, it's rising, but gravity is already pulling it back down. It slows, it stops, it falls. The universe, scientists believed, worked the same way. The Big Bang threw everything outward. Gravity was pulling it back. The expansion had to be slowing down. This wasn't speculation, it was physics. Gravity is an attractive force. It pulls, it does not push. And in a universe filled with matter, stars, galaxies, gas, dust, dark matter, gravity should dominate the large-scale behavior of space itself. Every model predicted deceleration. Every theory required it. The only disagreement was about degree. And then, in the late 1990s, everything changed. Two independent teams of astronomers were studying distant supernovae, Type 1a supernovae, to be specific. These are exploding white dwarf stars that have reached a critical mass, triggering a thermonuclear detonation. What makes them special is their consistency. Because they always explode at roughly the same mass threshold, they always release roughly the same amount of energy. They shine with nearly identical brightness. This makes them extraordinarily useful. If you know how bright something actually is, and you measure how bright it appears from Earth, you can calculate how far away it is. Astronomers call these objects standard candles. Type 1. A supernovae are among the brightest standard candles in the universe, visible across billions of light years. But there's another measurement you can make. When light travels through expanding space, its wavelength gets stretched. The farther the light has traveled, the more it's stretched. This stretching shifts the light toward the red end of the spectrum, a redshift. By measuring the redshift of a supernova's light, you can determine how much the universe has expanded since that light was emitted. Put these two measurements together, distance and redshift, and you can reconstruct the expansion history of the universe. You can see how fast space was expanding at different points in the past. The teams expected to find deceleration. They were trying to measure how much the expansion had slowed over billions of years. They wanted to determine the universe's fate. Would it expand forever or eventually collapse? The data told them something else entirely. The distant supernovae were dimmer than expected. That meant they were farther away than they should have been. If the universe had been decelerating, those galaxies would be closer, but they weren't. They were farther, which meant that in the past, when that light was emitted, the universe was expanding more slowly than it is today. Expansion had not slowed down. It had sped up. The scientists were stunned. This violated every expectation. They checked their instruments. They recalibrated. They reviewed their statistical methods. They looked for contamination in their data. Dust between us and the supernovae that might dim the light, making them appear farther than they were. They considered every possible source of error. Other teams independently verified the results. The measurements held. The universe was not decelerating. It was accelerating. This should not have been possible. In a universe governed by gravity, there is no mechanism for acceleration. Gravity attracts. It slows expansion. It does not speed it up. And yet, on the largest scales, something was overpowering gravity. Something was pushing space apart with increasing strength. They called it dark energy. The name is deliberately vague. It is a placeholder, an admission of ignorance. Dark because it does not emit, absorb, or reflect light. We cannot see it with telescopes. Energy because it behaves like a form of energy density that fills space, creating a kind of pressure. But beyond that, we know almost nothing. Dark energy is not like the matter we're familiar with. It does not clump into galaxies or stars. It does not seem to interact with ordinary matter or even dark matter through any force except gravity. It does not dilute as the universe expands, or if it does, not in the way normal matter and energy dilute. Instead, it appears to maintain a constant density, even as space grows. We do not observe dark energy directly. We have never detected a particle of it. We have never measured it in a laboratory. Everything we know comes from its gravitational effects on the universe as a whole. We see it in the motion of distant galaxies, accelerating away from us. We see it in the geometry of space, measured through the cosmic microwave background, the faint radiation left over from the Big Bang. We see it in the large-scale structure of the universe, the way galaxies and galaxy clusters are distributed. Every independent line of evidence points to the same conclusion. Roughly 70% of the total energy content of the universe is dark energy. Not dark matter, not ordinary matter, not radiation. Something else. Something we do not understand. And it is winning. One of the leading explanations is that space itself carries energy, that the vacuum is not truly empty. Quantum field theory predicts that even in a perfect vacuum, particles and antiparticles constantly flicker into and out of existence. These fluctuations might contribute a baseline energy to every point in space, a kind of vacuum energy. If this energy has a repulsive gravitational effect, and certain models suggest it could, then it would push space apart. Here's where it gets strange. When the universe expands, ordinary matter spreads out. Galaxies move farther apart. The density of matter decreases. The same is true for radiation. But if space itself carries energy, then as the universe expands and creates more space, it also creates more energy. The density of vacuum energy does not decrease. It stays constant. This means that as the universe grows, the total amount of dark energy increases. Not because dark energy is being created, but because there is now more space, and space itself is the source. In the early universe, when everything was packed tightly together, ordinary matter and radiation dominated. Their gravity was strong enough to overcome the effects of dark energy. The universe was still decelerating, just as expected. But as the universe expanded, matter and radiation diluted. Their density dropped. Their gravitational pull weakened. Meanwhile, dark energy remained constant. Eventually, a few billion years ago, dark energy became the dominant force. Gravity lost its grip. Expansion began to accelerate, and it has been accelerating ever since. This is a runaway process. The more the universe expands, the more space there is. The more space there is, the more dark energy there is. The more dark energy there is, the faster expansion accelerates, which creates even more space, and so on. There is no mechanism to stop it. If dark energy behaves as a cosmological constant, unchanging, eternal, the universe will continue accelerating forever. The future in this scenario is bleak but slow. Over the next tens of billions of years, galaxies outside our local group will drift farther and farther away. Their light will be red-shifted beyond detection. Eventually, they will cross the cosmic horizon, the boundary beyond which light can no longer reach us, no matter how long we wait. One by one, galaxies will vanish from the observable universe. Not because they've been destroyed, but because space between us and them is expanding faster than light can travel. 1 trillion years from now, an observer in the Milky Way, if such an observer could exist, would see a very different sky. No distant galaxies, no cosmic microwave background. Just the local group, the Milky Way, Andromeda, and a few smaller galaxies bound together by gravity, isolated in an expanding void. Stars will continue to form from remaining gas, but the supply is finite. Eventually, the gas runs out. Stars burn their fuel and die. Red dwarfs, the longest-lived stars, can burn for trillions of years, but even they will eventually fade. One by one, the lights go out. In the far future, tens of trillions of years from now, the universe will be dark, cold, Empty. Stars will be replaced by black holes, white dwarfs, and neutron stars. Even these will eventually decay, radiate away their energy, and disappear. What remains will be a thin soup of particles spread across an incomprehensibly vast space, with nothing to see, nothing to do, no structure, no complexity, no life. This is called heat death. The universe does not end in fire. It fades into eternal stillness. But there is another possibility, a worse one. What if dark energy is not constant? What if it grows stronger over time? This is not ruled out by current observations. We have only been measuring dark energy for a few decades. We know it exists now, and we know it existed in the recent past, but we do not know how it will behave in the deep future. If the density of dark energy increases, not just the total amount, but the density in every cubic meter of space, then acceleration becomes more extreme. This scenario is called phantom energy, and if it's real, the universe does not fade. It rips apart. This is the Big Rip. It begins the same way. Galaxies accelerate away from each other. The cosmic web breaks apart. Clusters dissolve. The night sky empties. But it doesn't stop there. As dark energy grows stronger, expansion accelerates more and more violently. Eventually, the rate of expansion becomes so extreme that it begins to overcome gravity on smaller and smaller scales. First, galaxy clusters can no longer hold together. They disintegrate. Then individual galaxies, stars that have orbited each other for billions of years, are torn apart, scattered into the void. Then solar systems, planets, which have been bound to their stars by gravity for eons, are pulled away. Earth, if it still existed, would drift into the darkness alone. Moons separate from planets, asteroids, comets, everything unbound. But expansion does not stop. As the acceleration grows even more severe, it begins to affect structures on smaller scales. Eventually, the expansion of space becomes so rapid that even the gravity holding planets together is overwhelmed. Rocky worlds begin to fracture. The ground beneath your feet, if you were standing on such a world, would begin to stretch. Mountains would crack. Continents would split. The planet would come apart. Then molecular bonds, the forces that hold molecules together, electromagnetic forces that have kept matter stable since atoms first formed, begin to fail against the violence of expanding space. Water breaks into hydrogen and oxygen. Rocks disintegrate into their constituent elements. Living tissue, if any remained, would dissolve at the molecular level. Then atoms themselves. The electromagnetic force binding electrons to nuclei is ripped apart. Atoms are ionized, stripped, reduced to bare nuclei, and free electrons scattered across space. Finally, in the last moments before the Big Rip, even atomic nuclei may be torn apart. Protons and neutrons, held together by the strong nuclear force, the most powerful force in nature, are separated. Quarks themselves might be liberated. The most fundamental structures of matter disassembled by the geometry of space. This does not happen over billions of years. Once the process reaches planets and smaller scales, it happens quickly. Some models suggest the final stages, from the destruction of planets to the ripping apart of atoms, could occur over mere months or even minutes. And then, nothing. Or rather, a universe so thoroughly destroyed that the concept of structure has no meaning. Just isolated fundamental particles, if even those can exist, scattered across an exponentially expanding void. The timeline for the Big Rip, if it happens at all, depends on how dark energy behaves. Current estimates, based on extremely uncertain projections, place it anywhere from 20 billion to over 100 billion years in the future. But these are speculative numbers built on models we do not fully trust. The truth is, we don't know. What we do know is that the possibility exists. It exists because the universe is accelerating. It exists because we do not understand what is causing that acceleration. It exists because dark energy could, in principle, grow stronger over time. And nothing in our current physics forbids it. We live in a strange moment in the history of the universe. The cosmos is currently at an age where it is still observable, still knowable. Galaxies are still visible in the night sky. The cosmic microwave background still carries information about the early universe. Stars are still forming, still shining, still dying in ways we can measure and understand. The large-scale structure of the universe, the cosmic web of filaments and voids, is still intact. This is temporary. Whether the universe fades slowly into heat death or tears itself apart in a big rip, the outcome is the same. The structure we see, the complexity that allows stars and planets and potentially life to exist, is not permanent. It is an interlude, a brief phase in a much longer story. Billions of years from now, civilizations, if they exist, will live in a universe profoundly different from ours. They will not see distant galaxies. They will not have access to the cosmic microwave background. They will not be able to study the large-scale structure of the universe because it will no longer be visible. Their cosmology will be limited to their local group of galaxies. They might not even realize the universe is expanding. They might not be able to discover the Big Bang. The evidence will have drifted beyond reach. We exist at a time when the universe can still be studied, when its history is still accessible, when the light from distant events can still reach us. This is not a privileged position in any moral or teleological sense. It is simply a fact. We happen to live during a window of cosmic transparency. That window is closing. Every second, galaxies accelerate a little farther away. Every moment, more light crosses the cosmic horizon and is lost forever. The universe is not just expanding, it is erasing its own history, and we are watching it happen. The discovery of accelerating expansion is not just a scientific milestone, it is a fundamental shift in how we understand the universe's fate. For most of human history, we didn't know the universe had a beginning. Then we discovered the Big Bang. For decades after that, we assumed the universe would either recollapse or coast to a stop. Now we know it will do neither. The universe is running away from itself, driven by something we cannot see, cannot touch, cannot explain. 70% of reality is made of a substance we know nothing about, and that substance is tearing the cosmos apart. We do not know why this is happening. We have names for it: dark energy, vacuum energy, cosmological constant, phantom energy. But names are not explanations. We have models, equations that fit the data, but models are not understanding. The fact is, we live in a universe where space itself is the dominant player, where emptiness has power, where the vacuum is not passive but active, pushing, accelerating, reshaping the entire structure of reality. And we have no idea why. This is unsettling, not because it threatens us directly. The Big Rip, if it occurs, is tens of billions of years away. Heat death is even farther. On human timescales, on the timescale of our sun, our galaxy, even the lifetime of all stars currently in existence, dark energy is almost irrelevant. It affects the motion of distant galaxies, but it does not affect the orbits of planets. It does not threaten Earth. It does not endanger life, but it changes everything about what the universe is and where it is going. It tells us that the cosmos is not winding down peacefully. It is not collapsing back into a singularity. It is accelerating into an unknown future, driven by forces we do not comprehend. The universe is not a closed system slowly reaching equilibrium. It is an open-ended process, expanding without limit, without purpose, without destination. And the most disturbing part is not what will happen, it's that we don't know what will happen. We don't know if dark energy is constant or changing. We don't know if the Big Rip is real or if the universe will simply fade. We don't know what dark energy is made of, where it comes from, or why it exists. We are living in a universe whose dominant component is a mystery, and that mystery will determine everything. The greatest question in cosmology used to be, how did the universe begin? We have made progress on that question. The Big Bang, cosmic inflation, the formation of the first atoms, the first stars. We have a rough outline of the story. It is incomplete, but it is a story. Now, the greatest question might be, how will the universe end? And on that question, we have almost nothing. Just observations that don't make sense. A force that shouldn't exist, and a future we cannot predict. Perhaps future generations will solve this. Perhaps they will discover what dark energy is, why it behaves the way it does, and what it means for the ultimate fate of reality. Perhaps they will find a way to test these ideas, to measure the properties of vacuum energy, to determine whether the Big Rip is real. Or perhaps they will live in a universe where the evidence has already disappeared, where the galaxies have drifted away, where the only physics they can study is local, where the grand questions of cosmology are no longer answerable because the data no longer exists. We do not know. What we do know is this. Right now, in this moment, the universe is still here, still visible, still full of light and structure and mystery. We can see it. We can measure it. We can ask questions about it. That will not always be true. The universe is accelerating. The distances are growing. The light is fading. And one day, far in the future, there will be nothing left to see. We live at a rare moment in cosmic history. A moment when the universe is old enough to be interesting, but young enough to still be observable. A moment when intelligent beings can look out into the night sky and see not just stars, but galaxies. Not just the present, but the past. Not just where we are, but where we came from. This is the window we have. This is the time we've been given. And the universe, indifferent and immense, continues to expand. Not slowing, not stopping, accelerating. The stars are still shining. The galaxies are still visible. The structure of the cosmos is still intact. But it is all moving away, faster and faster, into the dark.